Hey everyone, take a look at this roller coaster POV footage. Notice how the car is at the very top? It's moving slowly, almost pausing. But when it drops, whoosh, it accelerates incredibly fast. Today, we are going to answer a fundamental physics question. Where did that sudden burst of speed come from? It wasn't magic, and it wasn't all kinetic energy. We are going to unlock the concept of potential energy, the stored energy waiting to be used. By the end of this lesson, you'll see that position itself dictates power. Are you ready to become energy detectives? You are already familiar with kinetic energy, ke the energy of movement. But what if something is perfectly still? Potential energy is stored energy. It's the energy an object has because of where it is, like height, or how it is shaped, like a stretched spring. We can think of PE as a kind of energy bank account. The higher the object, or the more compressed it is, the bigger the deposit. These stored forms of energy are what dictate the motion we see in the real world, from roller coasters to jumping. When we talk about gravitational potential energy, we are simply asking, how much energy is stored just because this object has mass and height? The formula is incredibly straightforward. U_g equals mass times gravity, 9.8 meters per square second, times the height. Remember the order. Make sure you know what each variable represents. M is in kilograms, g is the acceleration due to gravity, and h is the vertical height. Since it's an energy measurement, our units are joules, J. Remember that 1 joule is 1 Newton meter, Nm. This is where many students get tripped up. Potential energy isn't an absolute value, it's a difference. It's the change in energy. Imagine we set the zero line at the ground. If we lift a book, its initial PE is 0, and its final PE is mgh. This is the most common setup. What if we set the zero line at the top of the bookshelf? Then the book's initial PE is now the new 0, and we calculate the change from there. The answer for the change stays the same. The key takeaway is that the change in potential energy, delta U, is what matters, not the absolute value. Let's pause and make sure this clicks. We have successfully mastered gravitational potential energy. Remember, the formula is U_g equals mgh, but the true power lies in understanding that P is relative. If I use the ceiling as my zero line, my calculated U_g will be negative compared to the ground, but the difference in energy between 2 points remains constant. This conceptual shift is crucial. Are you ready to move from gravity to something much more springy? If gravity is about height, elastic PE is about shape. This energy is stored when you compress or stretch a spring. Hooke's law tells us the force needed to stretch or compress a spring, F equals K delta X. The negative sign just means the force is restorative. To find the stored energy, we integrate that force over the distance, which gives us this beautiful formula. U_s equals 1/2 K delta X superscript 2. The first key thing to notice is this square on the displacement, delta X superscript 2. This is huge. Because of the squared term, small changes in compression or stretch lead to rapid changes in stored energy. This is a vital distinction from linear forces. Let's look at an example. If we compress a spring by 0.1 meter, we store a certain amount of energy. If we compress it by 0.2 meters, we store 4 times that amount. The equilibrium point, where the spring is neither stretched nor compressed, is our 0 point for potential energy, just like the ground was for gravity. This principle is used everywhere, from shock absorbers in cars to the mechanism in a crossbow. This is the grand unifying concept. If there is no friction or air resistance, the total energy of the system, kinetic plus all potential, will never change. Think of it as a perfect energy accounting book. If U_g decreases, Ke must increase by a matching amount, and vice versa. In the real world, however, friction acts as a non-conservative force. It always converts some of that mechanical energy into unusable thermal energy. We always start by listing all the energy forms, Ke movement, U_g height, and U_s spring compression. This is a straightforward calculation to test your understanding of the fundamental formula. We are only considering gravity here. We plug in the numbers. Mass is 2 kilograms, g is 9.8 meters per square second, and the height is 5 meters. Make sure your units are all standard SI units. Let's calculate. 2 multiplied by 9.8 which is 19.6, and then 19.6 multiplied by 5. It's 98. Therefore, the stored gravitational potential energy is 98 joules. The units confirm we calculated an energy value. Time to the spring. Remember, this is about the energy stored due to deformation. We use the spring constant, K, and the displacement, delta x. First, we square the displacement. 0.1 meters squared is 0.01 square meters. Next, we multiply 0.5 by 300, which is 150. Finally, we multiply 150 by 0.01. This results in 1.5. The unit is joules. So, the compressed spring stores 1.5 joules of elastic potential energy. Notice how the units cancel out to leave joules. This is the classic example. At the top, all the energy is potential energy, U_g. At the bottom, all that potential energy has been converted into kinetic energy, Ki. We set the 0 point, H equals 0, at the bottom, so the entire initial energy is U_g. We calculate U_g, 500 kilograms asterisk 9.8 meters per square second asterisk 40 m. That's a lot of energy. We set this total energy equal to the final Ke. Total energy equals 1/2 m v superscript 2. We solve for v. Solving for v equals square root 2gh. Plugging in the numbers gives us 28.0 meters per second. The energy never disappeared. It just changed form. Here we combine two concepts, elastic PE and Ke. The energy stored in the compressed spring is entirely converted into the kinetic energy of the launched ball. First, we calculate the stored energy, 1/2 by 500 asterisk 0.2, superscript 2 equals 10 joules. This is our total converted energy. Now we set 10 joules equal to 1/2 by 0.05 kilograms asterisk v superscript 2. Solving for v, we find v superscript 2 equals 200, so v equals 20 meters per second. This shows that the stored energy in the spring dictates the speed of the object it launches. The spring is the power source. This is a common trap. Just because we can't measure motion, Ke equals 0, it doesn't mean there's no energy. We must consider its position. A book resting on a shelf has gravitational potential energy. If the shelf were magically removed, that stored energy would be released. Think of it this way. The height itself is a measure of potential. The object is simply positioned to have energy. So, remember, zero velocity does not imply zero energy if the object is elevated or deformed. This is a high-level concept, but crucial for understanding the depth of physics. When we calculate U_g equals mgh, we are really calculating the energy of the system formed by the mass and the Earth. The Earth's gravitational field is doing the work that gives the mass its potential. It's a mutual relationship. This is why when we discuss potential energy, we are always discussing the system, not just the isolated object. The surroundings matter. Always ask yourself, what components are interacting here? The answer defines your system. Roller coasters are perfect real-world demonstrations of energy conversion. The goal is to drop the car high enough to maximize U_g. The more potential energy they build into the initial lift hill, the more kinetic energy they can generate later in the ride, allowing for greater speed. Physics isn't just theory. It's the core constraint for structural engineering. They must ensure the energy conversion is safe and predictable. Understanding the energy budget allows us to predict the speed and impact forces at the bottom of the steepest drop. When you jump, you first convert gravitational PE into kinetic energy until you hit the cord. This is the initial conversion. The moment the cord stretches, it acts like a massive spring, and the kinetic energy is abruptly converted into elastic potential energy. This slows you down. As you bounce, the energy swings back and forth. U_s dollar backslash right arrow dollar Ke dollar backslash right arrow dollar U_s. This oscillation is the heart of the system. This whole process beautifully demonstrates the principle of energy conservation in action, even with the added complexity of elasticity. Let's put the formulas into practice. We assume mass cancels out, so we only need G and H. This is a direct test of the energy conservation principle. Initial potential energy, m asterisk 9.8 meters per square second asterisk 10 m. Final kinetic energy, 1/2 mv superscript 2. We set them equal. The mass cancels out, leaving 9.8 asterisk 10 equals 1/2 v superscript 2. So, 98 is equal to 0.5 v superscript 2. Solving for v gives us 19.8 meters per second. Always remember to check your units. Since we started with meters and seconds, our final velocity is in meters per second. This one combines elastic and kinetic energy. The stored energy in the spring is the total energy available to launch the mass. First, calculate the stored energy, 1/2 by 200 newtons per meter asterisk, 0.1 m, superscript 2 equals 1 joule. This is our total energy. Next, we set 1 joule equal to 1/2 by 1 kilogram asterisk v superscript 2. Solving for v, 1 is equal to 0.5 asterisk v superscript 2, so v superscript 2 equals 2. V equals 1.41 meters per second. This confirms that the potential energy, whether from height or compression, determines the maximum speed of the released object. We covered a lot of ground today, moving from the simple height formula to the complex spring formula, and finally uniting them all under the umbrella of energy conservation. Remember the main idea. Energy is simply transferred. It's not created or destroyed. It just changes its form, from the potential energy of a high point to the kinetic energy of a fast object. You are now equipped to analyze energy in almost any physical system. Let's take a final look at the key takeaways. The most important concept to keep in your mind is the zero line. Don't get fixated on the numerical value of u_g. Focus on the change in u_g. Secondly, remember that we are analyzing a system, the object, and the Earth, when calculating PE. By mastering these concepts, you've taken a huge step in your physics journey, ready for more complex topics. Today, we didn't just learn formulas. We learned how to think like a physicist. We saw how position and configuration dictate the power available for motion. You learned that the relationship between energy forms is predictable and quantifiable. Use these analogies, the spring, the roller coaster, to keep these abstract concepts concrete in your mind. Great work, everyone. To deepen your understanding, the next natural step is to look at electric potential energy. Just like gravity, electric forces store energy based on distance. We also need to tackle non-conservative forces, particularly friction. These forces introduce energy loss, which is crucial for real-world accuracy. I highly recommend tackling more problems that involve both u_g and u_s, and where friction is present. This is where the full power of energy accounting comes into play. Keep practicing the energy conservation equation. It is the cornerstone of classical mechanics. Keep asking, where did this energy go? Imagine a simple pendulum, like a clock weight. When we pull it back to its maximum height, we are storing potential energy. This is the starting point, where speed is 0, so kinetic energy is 0. The height, h, determines how much stored energy we have. As the ball swings down, that stored gravitational potential energy begins to convert into kinetic energy, the energy of motion. At the bottom of its arc, the height is 0, our reference point, meaning PE is 0, and all the initial potential energy has been converted into maximum speed. This conversion is the core principle of energy transfer, making the pendulum a perfect example of energy conservation in action. We can calculate the energy at any point using simple trigonometry and the conservation equation. Think about a giant roller coaster. When the car reaches the peak, it has maximum potential energy because it's high up. But since it's momentarily stopped, its kinetic energy is 0. As the track drops, gravity is doing work, and that work is converting the stored gravitational potential energy into energy of motion. When the coaster reaches the lowest point of the main drop, the valley, it has traveled the greatest vertical distance, but it has also achieved its maximum speed. This speed is the point where almost all the initial potential energy has been converted into kinetic energy. This example is powerful because it shows that while the total energy remains constant, ignoring friction, the form of the energy changes dramatically as the coaster car moves. This is where things get complex, but also really cool. Imagine hanging a weight from a spring, like a spring scale. Now, we pull the weight down and release it. Here, the total mechanical energy is the sum of three things: gravitational potential energy, due to height; elastic potential energy, due to stretching the spring; and kinetic energy, due to movement. As the weight moves, the spring gets stretched and compressed, and its energy changes, while the height also changes. The weight will oscillate up and down, and if there's no friction, the total energy, P_gravity plus P_spring plus Ke, will remain absolutely constant, demonstrating the power of energy conservation in a coupled system. The trebuchet was an incredibly sophisticated machine that relied entirely on potential energy. When the massive counterweight was lifted high up, it stored huge amounts of gravitational potential energy. When the mechanism was released, gravity pulled that weight down rapidly. This sudden, controlled fall of the massive weight performed work on the arm, converting the stored PE into massive rotational kinetic energy. This rotation was then transferred to the projectile, launching it with immense force. It's a perfect historical example of how engineers harnessed the potential energy stored by height and mass to achieve a powerful, targeted application. Every archer knows this feeling. When you draw a bowstring back, you are doing mechanical work on the string, and that work is stored as elastic potential energy. The tension you feel is the stored energy. The amount of energy you store depends on how far you pull the string and how stiff the bow is. When you release the string, that stored elastic potential energy is instantaneously converted into the kinetic energy of the arrow. This process is a rapid, efficient transfer of stored energy, allowing the arrow to fly with maximum speed and power. It's a beautiful, athletic display of physics in action. For centuries, people understood that doing work required effort, but they didn't have a single, unified concept to describe the capacity to do work, which is what we call energy. Key figures like Robert Hooke studied elasticity, helping to quantify stored potential energy in springs. Later, scientists like James Prescott Joule performed meticulous experiments that definitively connected work done by heat, friction, to mechanical work. This helped solidify the realization that energy is a conserved property. It changes form, but it never disappears. This historical understanding moved physics from simply describing forces to understanding the fundamental accounting of energy. Let's work through a problem together. A rock is dropped from a cliff of height h. We want to know what percentage of its total energy it has at a specific height, y. Think back to the conservation of energy formula. E_total equals PE plus KE. If we set the ground as our zero reference point, the total energy is simply P_initial. At height, y, the potential energy is P_y and the kinetic energy is K_y. Since E_total must be constant, we know that P_y plus K_y equals P_initial. To find the percentage of PE, we calculate P_y slash E_total asterisk 100%. Take a moment to set up the variables in your head. Remember that y is the height and g is the acceleration due to gravity. Keep those terms clear in your equation. This problem focuses purely on elastic potential energy. We are given a spring constant, K, which tells us how stiff the spring is, and a stretch distance, x. The formula is PE equals 1/2 asterisk K asterisk x superscript 2. Let's plug in the numbers. K is 50 newtons per meter, and x is 0.2 m. First, calculate x squared. 0.2 times 0.2 is equal to 0.04. Next, multiply this by K. 50 times 0.04 is equal to 2. Finally, take half of that result. 2 divided by 2 is equal to 1. The stored potential energy is 1 joule. The key takeaway here is that the energy stored is proportional to the square of the distance stretched, meaning pulling it twice as far stores 4 times the energy. Here is a multi-step problem. A block starts at height h and slides all the way down a ramp to the ground. At the top, it has maximum PE and 0 speed. At the bottom, it has 0 PE and maximum KE. We use the conservation principle, P_initial equals K_final. We know P_initial equals mgh, and K_final equals 1/2 asterisk m asterisk v superscript 2. So we set mgh equals 1/2 asterisk m asterisk v superscript 2. Notice that m, mass, is on both sides, so it cancels out. This tells us the final speed doesn't depend on the mass of the object. Now, we can solve for v and find that v equals 2 asterisk g asterisk h. a simple yet powerful demonstration of physics. A common mistake is incorrectly setting the reference point for gravitational potential energy. Remember, PE equals mgh. If you choose the ground as your zero reference point, then the ground's PE is 0. If you choose the top of the cliff as your zero reference point, then the ground's PE is the negative of the total height. Always be explicit about where you set $h equals $0 at the start of the problem. Another mistake is confusing work and potential energy. Work is done by a force over a distance. Potential energy is the stored energy due to position or tension. They are related, but they are not the same thing. Careful definition is key to solving these problems accurately. Potential energy and kinetic energy are crucial, but they are just parts of a bigger picture. Let's connect this to momentum. $P equals mv$. Momentum tells you how much oomph an object has, regardless of its speed or mass. However, energy tells you what the object can do. Finally, let's talk about power. Power is the ultimate performance metric. It's energy per unit time. If two people lift the same weight, the one who does it faster has more power. Think of a sprinter versus a weightlifter. The sprinter has much higher power, even though their peak force might be lower. Understanding power helps us analyze efficiency and performance in everything from engines to human muscles. You've mastered the concept of stored energy, which is fantastic. But physics is a continuous journey. The next critical step is mastering the work-energy theorem. This theorem is a bridge. It states that the net work done on an object equals the change in its kinetic energy, $text work equals \delta key $. This provides a calculation shortcut. After that, we move into rotational motion. Instead of simple up and down falls, we consider spinning things, and instead of gravity, we use torque. Finally, we tackle collisions. While energy is often conserved, in certain collisions, like two cars crashing, some energy is lost as heat or sound. Studying these topics will give you a full, comprehensive understanding of how energy interacts in the real world. Let's take a deep breath and quickly review the core concepts. Remember the difference between PE and KE. PE is about where you are or how stretched you are. KE is about how fast you are going. The beauty of physics is that the total energy, the overall capacity, is conserved. This means the energy isn't created or destroyed, it just changes its costume. If you are swinging a ball, the PE at the top is entirely converted into KE at the bottom. If you are stretching a spring, the energy is stored elastically. Understanding this constant accounting is the foundation for almost all advanced physics, from orbital mechanics to engine design. To cement your understanding, let's compare two different types of stored energy. Think of a stretched spring. Its potential energy is stored through tension. It wants to snap back to its natural length. Now, think of a massive waterfall. The water held high up has gravitational potential energy. Both systems are potential energy sources, but the mechanism of storage is different. When the spring is released, it does work by contracting. When the water falls, gravity does work by pulling it downward. In both cases, the potential energy is the source of the force that ultimately does useful work, whether that work is compressing a cushion or generating hydroelectric power. Since you like sports, let's connect this directly. When a pitcher winds up, they are building up potential energy in their muscles. They are storing elastic and gravitational potential energy. When they release the ball, that stored energy converts into the kinetic energy of the pitch. Similarly, in a jumping sport, the PE stored at the peak of the jump is converted into vertical KE. The goal for any athlete, physically speaking, is to maximize the efficiency of this energy conversion. The faster and higher you can move, the more efficiently you convert your stored potential energy into useful kinetic energy. Physics is literally the blueprint for peak athleticism. To wrap up this detailed exploration, let's keep these formulas front and center. Remember, total energy is the sum of all forms. Gravitational potential energy, mgh, elastic potential energy, 1/2 kx superscript 2, and kinetic energy, 1/2 mv superscript 2. The single most important concept to take away is the law of conservation of energy. This law is a bedrock principle of physics. Energy cannot be created or destroyed, only transformed. Whether you are watching a roller coaster, swinging a pendulum, or even just throwing a ball, You are witnessing energy transforming from one form to another, but the total amount remains perfectly constant.